Okay, so I am going to talk about Bayesian optimization for state engineering of quantum gases. So I'm coming from the Leibniz University of Hanover. I'm working together in the group of Mr. Galul in the Institute for Quantum Optics. And this work is a shared work together with Victor Martinez La Huerta and LLER, of course. Which you will find here, but also a collaboration with colleagues from Berlin, Ivan Sekulic, Sven Berger, and Philipp Emanuel Schneider, which are somehow our experts for Bayesian optimization. And from their starting point, we developed together these methods further. So first, I would like to set the stage, what I mean when I talk about Bayesian, when I talk about state engineering. So when I talk about state engineering, we concretely prepare our BC for atom interferometry. And how we do it is we have this atom chip here, and we have a starting trap with the BC in its ground state, and we want to transport it to another trap where we then want to release it and want to start the atom interferometry sequence. But we want to have this BC with a set of specific properties in this final trap. And here there are different ways how to design these transports. One well-known way is called shortcut to adiabaticity, STA. So what this does is it reduces the extent of mass oscillation. And this was even successfully implemented in space on Cal and published by Nasser et al. And what you see is that you have a very good control over the in-trap oscillation after the transport. So that reaches levels up to residual oscillation of only 68 plus minus 72 nanometers. So very small oscillations. Now the question, when this STA method works so well for defining a transport, why do we even need another optimization approach? And the reason that I will give you here is we have some common goals also in this community, I think, for example, fundamental physics tests. One of these would be an Einstein equivalence principle test, where we have rubidium and we have potassium, and we want to drop these and measure their differential acceleration. But the difference now is we have two kinds of atoms, two BCs at the same time, and in space, if you have the same trap, everything is mingled together. So we still have to reach a very precise control still. So here, published last year, together with JBL, we realized, or we performed a dual-speed atom interferometry example in space. But even for this example, and we only reached 0.5 milliseconds in interferometer time, you see that this contrast drops to 0.2 already. This is 0.5 milliseconds. And we saw that we want to reach something like 25 seconds for these fundamental physics tests. So we are far away. And the first thing that is the reason for this is we have very bad center of mass control and control over the size oscillations. So we need to improve this. Why do we have such bad control? This is because for no interactions, we can work in the so-called Thomas Fermi regime. So we just decouple the center of mass motion from the size oscillations. These are two very cheap differential equations that we can easily solve, and you end up with these dynamics here. But if you now include interactions, this becomes much more complicated. You cannot disentangle those anymore, and you have to solve the 3D Gross-Mitajewski equation, which can be numerically very expensive. So what you see here, for example, is that you get these oscillations in center of mass, but you also get vastly different size dynamics. So the answer to why do we need another optimization approach is we need precision on the one hand, and we have complex systems on the other hand. And precision meaning, for example, for these fundamental physics tests, and with complex, what I mean is we have to solve a GPE, a 3D GPE, which can take up to minutes. So our state engineering goals that I will discuss here are fourfold. So we want to control the center of mass dynamics. We can do this easily with STA, that's not a problem. We want to control the size dynamics, which already is a problem with STA. But there is, and I guess you all know about this because it's vastly used, OCT, optimal control theory. We can control the size dynamics with that. But we can only do it for harmonic potentials. And in our realistic experiments with these atom-ship potentials, we don't have harmonic potentials, we have non-harmonic potentials. And also, we have interspecies interactions. Also, both of these methods would have a lot of difficulties to incorporate. The STA doesn't only have difficulties, it's really nearly impossible, I would say, because these are based on an analytical solution which you can just not have for these cases. And then the OCT could in principle do it. It's just a black box approach, but it relies on a lot of iterations. And if you have a simulation that takes up to minutes, and you have maybe a million iterations that you need, or 10,000, 100,000, then this gets very demanding. So we want to improve this. So the setup for these results for today is one that we took from these OCT results, because we wanted to test our new optimization approach on this very simple case. We do not use now a GPE or anything. We just use another optimization approach and see how does the convergence look like, is it in general a good approach, and so on. So what we have is we do the VC simulation, the Thomas Fermi regime, we decouple these two properties. And then we have this objective function, the optimization goal. And this corresponds of three terms. It's a classical energy, it's a quantum energy, and it's an additional term. These in the classical energy, what we mean is we mean center of mass oscillations. And in the quantum energy, we mean these breathing modes. The third part is one already that usually you don't really want to have, but in OCT you have it, because you have to avoid going too far in these potentials that you assume to be harmonic, because if you go too far in a realistic experiment, you run out of the harmonic regime, and then your optimization just fails. Therefore, we have this term to counteract this. Sorry, I didn't show these, but yeah, they are. So just as an example that you get a feeling for what we do, here on the right corner, you see the magnetic field ramp, a time-dependent ramp, which is not optimized here now. And we look at the center of mass dynamics. And what you see with the center of mass dynamics is that you get on the left plot in the frame of the transported ramp, of the transported trap, oscillations. And you see after the transport, after 150 milliseconds, you still get oscillations. And then, of course, you also get them in the velocity. This shows the Thomas Fermi size. So these are these breathing modes. And you see exactly the same thing. But what we want to do now is we want to reduce this part of the objective function. And with this, we would effectively reduce these oscillations. So we do this with multi-output Bayesian optimization. So this is our new contribution now. And it consists out of 4 steps. Step 1 is you need to find a parameter space that you can efficiently represent this ramp. Because what OCT, for example, does, it has 10,000 points. But if you now try global optimization on 10,000 parameters, I think we all know this is going to be very, very difficult. Therefore, we define another parameterization basis, and we use B-splines, which are just a set of connected polynomial functions of some given order. And then comes the interesting part, and that is we put it into the BEC simulation. And this can now be just the Thomas-Dölby regime, as in our test case here, or this can take up to minutes if you solve the GP. And out of this, you get your BEC properties. And this is already now the next step. What is meant by multi-output? So multi-output means we don't directly learn and just get out of the simulation the objective function, but we really get the BEC properties. We get the physics out of the system. And then we train a surrogate model. We use Gaussian processes for that. But the important part of the surrogate model is you get to put into this Gaussian process an input parameter that defines your RAM, and you get out the expected BEC property plus minus some uncertainty, because of course this Gaussian process isn't perfect from a finite set of data. So what you do is you have this set of test cases. You run, for example, 10 BEC simulations with 10 parameters. You have 10 of these sets here, and then based on this, you train the surrogate model. But what does this Gaussian prediction actually mean? So to explain this, what you can look at is you have this red line here. This red line is just in some quantity with just 1D parameter space function of this parameter. Then here you can see it, but there will be points that you can actually see. There is an observation, and this dotted line here plus this gray area is now the prediction of the Gaussian process. So from only one data point, of course, doesn't know a lot about the of this landscape here, but it tells you, okay, I think the value here is that value here with the dotted line, and this is the 1 sigma uncertainty of this prediction. But now what you do is you sample this a bit. So in the beginning, it's not super interesting where you sample, but then at some point, let's say after this now, what we will do in this next step is we will use this Gaussian process. And using this Gaussian process, we do a global optimization. And we do this by looking at two effects. Either we look for a point which is rather small, has a small value of the Gaussian process prediction, which would be here, or here, and then we look there and take the next observation there, or we go and look in an area where there's a big uncertainty. So from guessing, I mean, I know what comes, but there are two ways. Either now it happens exploitation, which is it's going to look somewhere with a smaller value here with smaller uncertainty, or exploration, where it looks in an area that has a higher value but a bigger uncertainty. Here it goes down here, and it becomes even clearer. The next value will be exploitation, so you look here. And with this, you build your model, you build your Gaussian process for understanding your landscape. So the next step, step number 3, is effectively what I just explained you. You now use this Gaussian process and do a normal optimization. Whatever gradient descent, particle swarm, whatever you want to do, you can mix them. You just do this optimization. But the cool thing here is, no matter how long this BEC simulation took, you have the surrogate model, and this takes basically no time. And then you take the best parameter out of this optimization loop here, you use it as the next observation point, and then you continue this loop. So the cool thing about this Bayesian optimization now is we learn physical quantities. So here, as an example, I show you one in blue, a scalar, a Gaussian process. This just learns the objective function. And in comparison, we learn 9 scalar Gaussian processes, which don't learn the objective function, but learn all the BEC properties. The size dynamics, so you have 3 sizes, you have three time derivatives of the size, and so on. And what you see is when you learn the physics instead of just the objective function, the optimization, the convergence is much better. And it is much better mainly because of this fact here. Mainly because there's a nonlinearity in the system. And it is much harder to find a model, a Gaussian process with accurate uncertainties. That's the main part. The uncertainties have to be good. If you have all these contributions in a squared way, and here 1 over R, for example, instead of just learning R, using these accurate predictions, and then just calculating from there the quantum energy. Therefore, you see that here this blue line, the quantum energy here, merely learns nothing because it can't understand how this looks. But for this, for example, which is linear, it doesn't make a difference. So we can do this. We can also do this with multi-output GPs now. That's the cool thing. This just makes it numerically more efficient. But in principle, it's the same thing as the scalar GPs. So now we compare this performance. When we compare the performance to OCT. And for OCT, what you saw is we have a lot of these iteration numbers. So you start, or they started here, with an STA ramp. And from there, they tried to optimize, in addition, these size oscillations. So therefore, they have a good classical energy in the beginning. It goes up while they try to find a better quantum energy, and then goes down again. And for this, even with a good starting point, they need 1,000 iterations until they converge to the eye. And then that still goes on a lot of optimization here. But at least they converged up to the 10 to the minus 1 nano-kb level or so. So we now use two different weights for each of these energies here, and we look at the result. What we see is, of course, based on the different factor here, either the quantum weight, so this 5 times 10 to the 5 is really good here, so this goes down, or if it's more balanced, they both go down in a much more balanced way. Now, the cool thing about Bayesian optimization is, because we have this really good understanding of the system, of the physics, and not only one objective function, is we can do a guided optimization. We can say, okay, I want this classical energy to be 10 to the minus 3 nanokelvin, want this quantum energy based on top of the ground state energy to be 10 to the minus 5, whatever. I just used here the best of what I could get with quantum, or what we just got with quantum and balanced. And we see this guidance even improves this and makes it better in all of those energies. So this is clearly a way, when you design an atom interferometry experiment, you say, okay, I want some control this property, I want other control this property, don't really care about getting much better in the others. So you use this guided optimization, and this can help you really a lot. So just to show you how this looks like now, maybe this is familiar. This was just a random pick from 40 iterations that has still oscillations. And after 500 iterations, it looks much better. We don't go here into, don't focus here now on exactly how this looks like. The main message here is just, it does what we expect. And it is able to give us these ramps here that we already know from STA and OCT, but we didn't tell Bayesian optimization what to do. There is no initialization or so. So the cool thing is also, if you give it a completely new problem, OCT needs a good starting point. Here it had a good starting point, but Bayesian optimization, at least for this problem, doesn't. So to sum this part up, for the state engineering goals. OCT has a lot of iterations. Yeah, if you have enough time, it's never too many iterations, but it has a lot. Multi-output Bayesian optimization has at least 10 times fewer iterations without a good initial starting point, which OCT had, and maybe more, but unfortunately, there wasn't a log plot in the results that we compared to. So this is our claim. What we now can do is we can use these fewer iterations and replace the cheap simulation with dual species 3D simulations. Unfortunately, I will not show you results now, but I will discuss a bit what I expect that comes up, what we have to think about, and so on. So, as an outlook, if we want to do 3D dual species state engineering, we now have to fuse a bit of our tools together. So what we have in Hanover is a pretty accurate atom chip simulation, which gives you not a harmonic trap, but you get a proper trap in 3D. You can combine it with this uatus.pi that we already heard about in the frame of Pixel. And this is a 3D GPU-based numerical solver. Normally, it is used for atom interferometry simulations, but it doesn't matter. You can use it for whatever potential. And then you get out a wave function, for example, for rubidium and potassium. And this black box here, you just put into this multi-output Bayesian optimization. And we expect it to work very similar. We will do it. And I hope these results will come out soon too. So what changes? Going from Thomas Fermi to GPE simulations. What changes is first the potential. So the harmonic traps that we just coupled, we just look at the set of mass oscillations and so on, for example, will be replaced by arbitrary traps. And we will also look then instead of the Hamiltonians of this directly, instead of trying to find other solutions. The second thing is the simulation output and of course the duration change. So the simulation output will be a wave function, which previously was just a set of parameters, and the iteration will increase. Now, I would expect something on the order of a minute, maybe up to 5 minutes, depending on your scenario. But what you can do the super easy way. So there might be better ways of doing this depending on your optimization goal and so on. But the cheapest way would just be to calculate back these properties of the wave function, but now from the wave function directly by taking expectation values and so on. So what changes is the BC simulation, it takes more time, and the BC properties, but you can get back the expected properties as usual. What doesn't change is even more interesting, because what doesn't change is first the time that you need to train the surrogate model. Even now that the GPE simulation takes a lot of more time, once you did this, or each iteration that you did this, the rest of the optimization takes exactly the same time. So the surrogate model training takes the same time. The global optimization takes exactly the same time because it uses the Gaussian process. So some exciting ideas, exciting to me, at least, as applications for this. One of those would be, we have these objective functions which have this classical and quantum energy, which we just took over for benchmarking, but I think this wouldn't be the way how you should go about this. Instead, you should optimize the sensitivity directly. And these are just two randomly selected equations, but they make one really good point. Here you have this phase, the rotation phase, based on the frame of your experiment that has a rotation, and you have a limitation for wavefront curvatures. And you see there are some properties in here. For example, a wavefront curvature R, your experimental goal, or your interferometer duration, which might change. You might design a mission with this, or change it in the meantime. But the physics of the system doesn't change. Because we learned the physics of the system and we didn't just optimize an objective function, we can recycle our Gaussian processes, our surrogate models, and just calculate this and optimize this again, without even having the heavy GPE simulations in between. Second one is you could go one step further, which is you can take this psi, the wave function, and put it into the next simulation step. You just simulate. Now you can do much more complicated things. You now just simulate the full interferometry sequence and the sensitivity from there. Another one would be for the exciting, oh no, this is, now I finished my sentence. For the exciting physics that Nathan Rundblatt does on the ISS in the Caudato lab, you could think about trying to get more homogeneous quantum bubbles. But of course, the simulations required to understand these physics is pretty complicated. So it's good to have an optimization that can still optimize this process, although it is highly computationally demanding. And then this one would be, you could also explore different mixture phases. So your objective function, your optimization goal, doesn't have to be zero motion, zero oscillation, whatever. It can also be something more interesting. So to sum up, we presented here a multi-output Bayesian optimization for state engineering of quantum gases. I invite you to look up the details here in this archive paper. We have three main results. First one, we have a general framework now for the state engineering. You just change one of these components, but everything still works. We reach our target state for this benchmark after a few hundred of iterations, which then allows us hopefully to use more demanding simulations. And we learn the physics. And I think this is one thing that always gets forgotten in these optimization routines, that you don't have a clue about the physics, and then you change one value in the objective function and you have to do everything again. So now we learn the physics and we can use them. So thanks for listening.
Thank you for the nice presentation. Is there a question? So let me start with one. Or there wasn't.
Thank you, Gabriel. Nice talk. One frustrating thing about some of these experiments that we would love to apply these techniques to is that not only are the clouds not Thomas Fermi, they're not even really GP because they have significant thermal fractions, or they might actually be thermal gases. Do you see a possibility for using some of these techniques with thermal gases or clouds that are maybe not pure BECs?
I know that your colleague Brandon Rhino performed some simulations, right? So these simulations, whatever you used, you could plug into this optimization. We in Hanover are no experts in the regime of doing thermal simulations, so I can't say much for this. But as long as there's some simulation and you have enough time to do a couple of hundred iterations, I'm pretty optimistic that you could do this.
Thank you, Gabriel. Excellent talk. Our question is, you have done all the simulation within this Thomas Fermi approach, right? And scaling. Can you do it directly for GP? That's the first. And second one is, of course, there's many phenomena when it actually sloshing. Whenever motion, you just also imprint the phase on the BC and so on. And it will be also interesting. Can you also catch up this type of phenomena?
Yes. So I think the answer to both is actually very similar. So It is not part of this paper. So here we just did Thomas Fermi because we wanted to benchmark the new optimization method. But this is a paper from my colleague, Annie Pishri, and we are doing all of what she did as well in a compatible way. So we can, and this we are good at, solve GPEs numerically, 3D systems with a lot of points in an efficient way. And if you use this, you get all these things like face imprints and so on. So now you have to think in the next step of what's your optimization goal. But if you go all the way to this idea that I shared here, where you say, okay, I want to even put this then into the next simulation, then all of what you included can be part of your optimization.
Yeah. Thanks for your talk. My question is that for the ST Quest satellite project, the position overlap of the position is need to be as small as micrometer. I think that. So what do you think the most challenge for the dual species bottom preparing for this high challenge experiments?
Yeah. So first, I think without solving the GPE, it will be very, very hard to do this. So we did this in a recent in this publication that I also shared another result for. And what we see is that if you don't control these, if you don't understand these, that you get these shifts of clouds without going into much detail now. But we see this experimentally. And what we also see then is that after already very short times, we lose the contrast. But I think in terms of the optimization, once we include the GPE, we can do this. We can reach these micrometer levels. But then for a mission like ST Quest, there are of course a lot of other difficulties. But in general, I think this is very well possible, and I think this is not this will not gonna hinder ST Quest or a similar proposal in succeeding.
Is there any further question? That doesn't seem to be the case, so let's thank both speakers again.